Hi, this video is for section 9.3, which is a hypothesis test for mean with sigma known, the population standard deviation known. So you're going to see a lot of similarities to chapter 8 with the confidence intervals, but there's also quite a bit of differences because hypothesis tests are not the same as confidence intervals, but we're going to make some similar choices on the calculator. So before we get started, I want to make sure you have that extra page that I put in the last section. And so it looks like this, the symbols used in chapter 9, because we're going to use this just to refer back to all the time. So we talked about the null and the alternative hypothesis, where the alternative is the claim. And we talked about the two-tailed, left-tailed, and right-tailed. But for this section and for all the sections after this, we need to talk about the reject region and the do not reject region. So for a right-tailed test, hopefully you can see, maybe I should make this bigger, see if it doesn't really help. Okay, so over here, a right-tailed test that's shaded on the right side. A left-tailed test is shaded on the left side. And a two-tailed test is shaded on both sides. If it lands in the plain white part, you do not reject the null. And that is true for left, right, and two-tailed. You do not reject the null in the unshaded part. In the shaded part, whether it's on the right, on the left, or both the right and the left because it's two-tailed, in the shaded part, you will reject the null. So we are going to draw these pictures today. We are going to talk about what rejecting the null means, and then we're gonna do the whole hypothesis test from start to finish. So let me see if I can remember what page. Ooh, I think I'm close. Okay. So one thing I did on this, you'll see, is I drew the picture to start because you know how terrible I am at drawing. I don't know why I didn't think of this earlier. Here's the picture. So now it'll be a lot easier to shade, and I don't have to be all wonky with my lines. Okay, so this one says, again, this is for sigma known. So this says a sales associate would like to test the claim that, and here's our claim, the average number of sales made by a sales associate per year is less than 600 sales. To test this claim, the sales associate collects data on a sample of 40, so that'll be our N, and a sample mean of 575, so that's our X bar, because sample mean is X bar. From past data, it is known that the population standard deviation is 76 sales. So this is where we know what sigma is. Assume the population is normally distributed, and it says as the alpha equals 0.025 level of significance, test the claim. Okay. So we're gonna not necessarily use everything in this example because it's just the beginning. But I just wanted to practice pulling things out. In fact, we're gonna use almost everything except for like the mean and the N. We'll do that calculation coming soon. Let's just talk about the new stuff. Well, it's not all new, but new for this chapter. So identify the null and alternative. So we have our null. Why is that so big? And our alternative, and our null is going to be, first of all, we're talking about mean. This whole section, we're talking about mean. So we have our mu, where's my drawing? My lovely mu, somewhere. Here she is. Mu for both of them. And then per the claim, we have 600 and also less than. Those are the two things we're going to take away from the claim. So the alternative is the less than 600. Mu is less than 600. And the null is equal to 600 because the null is always equal. Okay, now this one says draw a picture using a p-value of 0.019. That part right there, we're going to put on hold. Like, what does it mean? Where did it come from? All this stuff. That's the part I'm giving you in this problem just to kind of get the basic structure of these tests. And then we will talk about what that means. Oh yeah, we'll figure out how to, you will figure out how to calculate that, I think by the third one, by the second page. Okay, so we have a p-value of 0.19 and we have our alpha over here at 0.025. Oh, I just realized I was doing this earlier and answers on the calculator. Can't show that. Okay, so number line, smaller numbers over there, bigger numbers over there. Also, this is a left-tailed test. So we got to think about that in terms of the number line left-tailed test. I'm just going to draw a line right here for starters because this, here's my whole dang picture. Okay, I'm going to draw a line to make a left-tailed test. And let's just shade it in while we're here. And shade. Oh gosh, okay, that's terrible. You can't go outside the line. Okay, shade. So the line is drawn at our alpha. So this line is drawn at 0.02. So along here, we have our P is 0.019. So we have to figure out where that lands on here. And so 0.019 is somewhere over here. It's somewhere to the left of 0.025. And therefore, it lands in our reject region. What in the white writing just happened right there? Why is it? Oh gosh. Oh, because I added the picture. Okay. I'll write it above the picture. Reject. No, this is, I don't know if I can draw an arrow because that picture's right there. And I think the white from the picture, this whole section, let's see if the arrow stays. Oh, the arrow stays. This whole section says to reject the null. So pause, not literally pause, but just hold that thought. This is the reject region for a left-tailed test. I'm going to jump to the last page real quick. So what we have is this middle scenario right here. Our cutoff line is at alpha, which is 0.025. And our p-value was less than alpha. So it's over here in the reject region. We are going to reject the null hypothesis. All right, carry on. So that's my picture. Now we are going to determine a conclusion and then interpret. We're going to interpret it and then determine the conclusion. Okay. So I don't know which one's the conclusion and which one is interpreting. Okay, yeah, that's that. Interpreting is the reject. I wrote it up there, but let's just write it down here too. We are rejecting the null. That's how I'm interpreting the picture because our p-value, our 0.019 landed in the reject region. Now, to determine the conclusion, we are going to say because we are rejecting the null, we are going to say there is sufficient evidence to support the claim that, okay, so let me just get back. I'm going to finish my sentence in a minute, but I just want to come back to the problem. Rejecting the null means this is not true. The null is not true. That means we want the alternative. So we will support the claim. We will support the alternative. We are not, no, we are rejecting it. Throw the top one in the trash. We want the bottom one, the alternative. So there is sufficient evidence to support the claim that, and let me scroll up a little more. The claim was that, and I highlighted it there at the top, the average number of sales made by a sales associate per year is less than 600 sales. So we either have sufficient evidence to support the claim or there is not sufficient evidence to support the claim, and then we write out the claim. So let me just talk through that one more time. We are rejecting the null because it landed in the reject region. Now, just a reminder, we are either rejecting or not rejecting the null. That's it. It's always about the null. So since we are rejecting the null, that means we are supporting, because the opposite of rejecting something is to support the other thing. We're supporting the alternative. And the alternative is always the claim, like the last video. Now do you see why I didn't do all these calculations in the middle? Because this is already a lot to take in. Let's practice it again, and then we'll get to the calculation. Okay, same thing. It'll be a little bit different because of the type of test and whatnot, but okay, let's see. We have an orthopedic surgeon would like to test the claim. Okay, so let's get our claim that the average healing time for a compression fracture is greater than 19 weeks. It's good to identify the claim for our null and alternative hypothesis in step A, but then by the time you get to step C and you need to write the conclusion, like, what's the claim again? So I like to identify the claim at the beginning for both those reasons. To test this claim, an orthopedic surgeon collects data on a sample of 30 patients, so we know N, again, we'll be using that soon, and records a sample mean of 19.1 weeks. From past data, it is known that the population standard deviation, so sigma, is 2.4. Assume the population is normally distributed at the alpha equals 0.01 level of significance. Test the claim. Okay, so we are going to identify the null and alternative, and then that's going to tell us how to draw the picture. So we have our null, we have our alternative, we have our mu, wrong button, mu, looks like a ghost wrote it, mu. Okay, mu is, where's our claim? The average healing time for a compression fracture is greater than 19 weeks. So always go to the alternative first. Mu is greater than 19 weeks. Therefore, the alternative is equal to 19 weeks. Null is always equal. Alternative is whatever the claim is. And since it's greater than, then we have a greater than. Okay, coming back here, we have greater than is a right-tailed test. So it's going to look like this picture right here. So let's draw our right-tailed test on the picture. Don't move that again. Okay, that's a little dramatic. Okay, stop. Let me just undo some things. Here we go. Let's try this again. Okay, perfect. We have that. We have our shading. Shade, shade, shade. Okay, and so our line is always drawn at alpha. So our line is drawn at 0.01. Okay, now because it's the right-tailed, things are backwards. So this is like 0 over here, and we have 0.01, and so our p-value is right here, 0.410. That's actually going to show up over, what did I use last time, an arrow? That's going to show up somewhere, stop it, over here. And, you know, somewhere on the number line. So we have 0.410. It falls into our do not reject region. So there's a rule that says if alpha, let me go up, show you what I'm talking about. If alpha is bigger than the p-value, we reject. And if alpha is less than the p-value, we do not reject. That's true. You might read it in some of the homework, but it's not going to match what it says in the calculator. So that's why I'm drawing it this way, because I want to match what it says in the calculator. So this is do not reject the null. Do not reject the null. So draw a picture is over here. Determine the conclusion and interpretation. So to interpret, we are going to say, I just copied that from last time, so we want to say do not reject the null. And then for our conclusion, hopefully it fits here, we are going to say there is not sufficient evidence to support the claim that, okay, so again, I'll get to the claim in a minute, but notice up here, when we reject it, there is sufficient evidence to support the alternative. When we cannot reject the null, so I'm not saying I love the null, I'm not saying the null is great, I'm just saying we don't have enough evidence to reject the null. So if we don't have enough evidence to reject the null, we also don't have enough evidence to support the claim. So there's not sufficient evidence to support the claim that, going back to the beginning, at the top, the average healing time for a compression fracture is greater than 19 weeks. Notice one little thing about this. In the answer, can I highlight what I typed? No. Okay, let me see if I could draw a box around it. The point is there's a knot right here. It doesn't like it when I do two things at once. Okay, anyway, do you see the knot right there? I can't highlight it. And there's a knot right there. Knots go together. This had no knot and no knot. Does that make sense? Reject the null, support the alternative. Do not reject the null, do not support the alternative. Okay. Hopefully that's starting to make a little sense. We saw one example of each, rejecting and not rejecting. Now, just to be clarified, this has nothing to do with the tail, left tail or right tail. It's not like left tail is always one answer and right tail is always another answer. I was just trying to mix up the different tails and also mix up the different answers. So the answer will always just depend on, did it fall in the white section or did it fall in the red section or the shaded reject region? Okay, so let's start from the very beginning. I'll show my calculator. Okay, well, not as graceful as I wanted, but here we go. It's like going on my other screen. Okay, perfect. Except now it is too zoomed in. So the CEO wants to determine if the training times had increased. So what are we determining? Training times had increased. Where's it? Hang on a second, I want to get it. Over the last year. Okay, it is going to kind of be in two pieces. The CEO sampled 10 new employees, and they found a sample mean of 87.9. Historically, they know that the time spent is normally distributed with an average of 85 minutes. So the way we're going to use that 85 minutes, because this is the historical, it's going to go over here. Have increased for employees over last year. We know last year was 85 minutes. So let me just put that information up at the top. Had increased for employees over last year, which was 85 minutes. Okay. The standard deviation was 1.9 minutes. Again, this is the population stat. Assume the population standard deviation is equal to this. So this is the population standard deviation. Use the calculator to test whether the time in training has increased over the last year. Okay. That's the same basic idea. I'll just underline it just so when we're writing the claim, we'll have a couple different ways. Over the last year, remember, which was 85 minutes. Okay, so what are the hypotheses? We have our null and we have our alternative. We are only talking about mu in this section. My mu's are getting worse. Okay. And we know that we're trying to claim that they've increased from the 85 that they were. They were 85. We want to see if they've increased, which is greater than. So our null is equal to both the 85. Draw a picture and label your p-value. Okay, so for starters, I am going to draw what I already know, and then we'll do the new stuff. So I know that this is a right-tailed test because it's greater than. This is going to do this to me every time. Right-tailed test, perfect. Shade in the greater than for the right tail. Stop it. There we go. Try this one more time. And the line is always marked with alpha. So this is 0.05. Okay, so now let's see how this looks on the calculator. I might need to make the screen a little bigger in a minute, but so we're at home. And we want to go, let me just refresh it so everything is all new for you, because this is what it'll look like on yours. So we have our calculation. We have our home, which says the calculation app. We want to go down to inference. So this is very similar choices on the calculator to confidence intervals. You've seen that this process is not similar to confidence intervals, but the calculator process is similar. So we go to inference. We have our tests. We're doing significance tests, in this case, a hypothesis test. This is one mean. We're only going to do one mean and one proportion. We're not doing two. And because we know the standard deviation, because we know sigma, the population standard deviation, we're going to use the z-test. And again, if you're so it's the same as confidence intervals. And let me just forward this a minute just to, I'm going to come back to this. Don't hit anything, just look at mine real quick. Right here, I say the wrong one. I said the wrong one, didn't I? No, I didn't. I said the right one. See right here, the population standard deviation is right here. So if you get to this point and it's asking you for the sample standard deviation, you pick the wrong one. So we want Z because we know the population standard deviation. Okay, so we're here, we chose Z. Now, our null hypothesis is that mu is equal to 85. So I hit OK and I type in 85. And once I do that, it'll automatically give me the mu equals. And now that I typed in the 85, this one has changed to 85, but it defaults to less than. So if you hit and can you hit OK? Yeah, you hit OK or enter, and we're going to go down to greater than because we want it to match what we have over here. Then we are going to, oops, we don't have a data set, we have statistics. So we know X bar, the sample mean was 87.9. We know the population standard deviation was 1.9. And we know N is 10. So in the calculator, I did not, well, in this part, the statistics part of the calculator, I did not put 85. 85 was on the last screen. This is all the other numbers besides 85 on this screen. And then our alpha, our significance level is 0.05. That's perfect. I'm going to go down, hit next. And then here's our Z value. Okay. And this is more what we're looking for is the P value. Now, I saw this mistake happening on project number 2, is that people are seeing this number and they think it's a big number, like almost 7, but it's actually a very, very tiny number. And the reason I know that is because of this E -7 is giving us scientific notation. So let me just, I'm going to delete this real quick. I just want to write it out so you can see. It's like saying 6.94 times 10 to the -7th power. That's what this -7 is. In other words, it is 0.0094, because if I moved the decimal 7 spaces to, or if I move the decimal to here, it would be 7 spaces. That's a very teeny tiny number. So where is that? Let me grab this. It is way over here. It is like very teeny tiny. it's so tiny that it's like not even existing, right? It's like super teeny tiny. Okay, I want to just pause for a second, and before I go on to the next screen, here it says Z is 4.82. So if you remember from chapter 6, and we do this, we've used Z throughout, zeros in the middle for the Z-score. And I said going out to 3 or -3 was pretty rare. We don't go beyond 3 and -3 very often. Well, this one's practically to 5. So it's super way, way, way out there because it's so far away from the middle 0. Okay, so let's see what that looks like on the calculator. And this is a really hard one to start with because it's so far away, but let's just see if we can get this shown up a little easier. So remember, P was all those zeros. Well, let's just look at Z for a minute. Z is 4.8. So here's 4. So here's 4.8. See where the Z is? That Z mark is the same. Everything past the Z mark is shaded for the P value. Again, this is hard to see because everything seems to be the same color at this point, but we have our reject region right here where alpha is. And then anything lying over here from this line over, we reject. So since Z is way over here, we are definitely going to reject the null. So let's move this guy over somewhere more useful. And all of my Zoom stuff wants to take over. Here we go. Perfect. We just need to not have false. So that was a lot of looking at stuff to say that we are going to reject the null because it is in the reject region. Kind of hard to read. There we go. So we will reject the null, and that means there is sufficient evidence to support the claim that training times have increased for employees. You could add the rest. You could say has increased for employees over the last year, which was 85 minutes. I was only including that to get our part A, our null and alternative hypothesis. It's not 100% necessary to have in the conclusion. It's just helpful to have it for part A. Okay, these are deceptively long, I would say, because see, this doesn't look like it takes up that much space. The amount of time that goes into these problems is a little longer than half a page looks like. So let's see, we have that. Okay, we'll see how far we get on this because I feel like this video is already going kind of long. So let's try this one more time. It says a CEO wanted to determine if the time responding to emails during the day had changed. The CEO randomly sampled 10 employees and asked how long they spent each day responding to emails, and they got a sample mean of 157 minutes. Historically, the time spent responding to emails, according to a previous survey, was 155 minutes. So there is our claim, or, well, that's part of our claim. And then the other part, they want to determine if the time responding had changed. So I'm just going to kind of combine those two thoughts. Is the time changed from 155 minutes? There's a standard deviation of 4.3 minutes. Assume the population is equal to historical. Use a calculator. Okay, and then here's our alpha. So it does not say greater than. It does not say less than. It says, did it change? Is it different? So different is going to be not equal, because equal means the same, so not equal means different. So we have our null. We have our alternative. We need our mu because we are in the mu section, but also we see lots of stuff about averages, standard deviation, and all that stuff. Those all go with mu's, just like in chapter 8. So this first one is going to be Oops, where's my text? Okay, where did that dot come from? Oh, what happened here? Why is there giant dots? Okay, let me just pause for a minute and redo this. Okay, give me my muse again. And we have equal to 155 or not equal to 155. So I'm going to write equal real quick, and then I'll go ahead and throw in my not, my dramatic not. It's not equal to 155. Why do we need that? Remember from the last video, not equal means it's a two-tailed test. It's on both sides. So we're going to have our alpha showing up on both sides. Oopsie. Where did my picture? Let's go back here. So I have two tails. I did this wrong every single time, right? You think I would learn better. So we're going to save that in. And it's not ever going to be on both sides. The answer will never be on both sides, but it's just giving us like two ranges. It can be either on this side or it can be on that side to reject it. We don't know which, so that's why we are using this. Okay, so we're gonna come over here. We'll get our p-value in a minute. I don't, because it wasn't given. So I go back to the beginning. I don't need to go all the way back to choose Z because we're still in the same section. So I come here to my null and alternative. My null is 155 and my alternative is not equal to 155. So I just hit enter or OK, and it lets me pick. Statistics, we'll do data set on the next one. Our sample mean is 157. Our population standard deviation was 4.3. Remember, we already used the 155, so that does not go on the screen. That was already used over here. Sample is 10. Alpha, this is a pretty common alpha, so you'll see that a lot. And our p-value is 0.141. We'll see that on the next screen. And so let me hit OK. Yes. Next. So let's just zoom into this real quick to talk about what's going on, and then we will draw it. So here, it's a little easier to see what's going on. We have our reject region shaded over here, alpha. Alpha, that's the slash, the gray shaded, and it's over here. So alpha tells us where the reject region is. P, which is 0.1413, it doesn't matter which side you look at it, they put it on both sides for us. Here, I can see that this is bigger than our alpha. So this is in the do not reject. This is bigger than my alpha, so this is in the do not reject. If I was going to reject, it would have to only be in the shaded part. So since it's over here, we will not reject our alpha. If P is greater than alpha, we do not reject. So let me go back to my screen over here. See, the problem is all my Zoom stuff pops up as soon as I move this thing. There we go. Right. So we have our P showing up. I wish I could just, oh, here's a little check, a little X. We'll put a little X. Our P is showing up right here. Okay. That's where our P is showing up. The line is just because it's not transparent, it's not showing up exactly where I want it, but you get the point because you can see it over here. Our p-value is 0.1413. And then our alpha was 0.05. So since P is bigger, it lands over here in the middle. I do want to point out over here, you can zoom in. If you can't, like, I mean, I want to use it to full screen. But if you're just looking at your phone and you can't see, you can hit the plus and the minus, and it will zoom in for you. So you can see exactly, okay, this is actually way far away from the shaded region. It's definitely a do not reject situation. And then you hit minus and it goes back to. Okay, so do not reject the null. That is how we are going to interpret this. And so, in other words, since we're not rejecting the null, there is not sufficient evidence to support the claim that, oh, here we go, the time responding to emails during the day had changed. Time of responding to emails during the day had. And if you want to say from 155 minutes, that's fine. You could put it in there, or you could just write exactly what the problem is. Either way. Okay, so I am just going to stop sharing for a minute because I want to see how the heck long this video is. Stop. Oh, cool. It doesn't tell me. So we are out here in Mysteryland. Okay, whatever. I at least need to show you one more because it's a totally different kind. Okay, so this one is different because it has a table. This one I just gave lots of space on because the table, they weren't going to both fit on the same page. So this is an HR employee is studying salaries and wants to test the claim that, here we go, here's our claim, the average HR director salary is different than 105,000. The HR employee selects a sample of 20 random HR employees and reports their salaries. Based on past studies, the HR employees determined that the population standard deviation, which is our sigma, is $32,000. The HR director conducts a one mean hypothesis test. Okay, 5% significance level, so there's our alpha, and there's our claim again, and here is our data. So our mean, or our null and alternative hypothesis. So we are talking about mean. I would say for the last time, but the next section is also mean. So, oh, golly, too big. And we are talking about different than, so we are back into our equals versus not equals. You could put it with a comma or without a comma, it doesn't matter. And so just as a reminder, come in and put your not equals on the alternative. Oh, it's attached to the mean. Okay, we're not going to be that picky. And so we're going to our calculator. Back to our hypotheses. You can type in these big numbers, 105,000. Well, you have to do it correctly though. Okay, 105,000. Again, it's in scientific notation. So 105E5 or 1.05, that's saying that if you put the decimal here and you count it over 5 spaces, 1, 2, 3, 4, 5. So it's the same number. It just writes it in scientific notation when it's so big that it doesn't fit. And you're going to notice all of these convert to scientific notation. It's okay. And it says not equal, so we're good to go. I'm going to this time use the data set. So my data set is, and now we're going to type, you know, this video is getting long. I'm going to pause it for a minute, and then you pause it at your leisure, type in the data set, and then we will come back and have the same data set. So let's see how to pause. Oh gosh, did I make a promise that I can't keep? Nope, wrong pause. Okay. Okay, probably didn't need to pause it. It wasn't really that time consuming to type those in, but let's just double check. Again, all of these are popping up in scientific notation. Most of them have a 5 because they're 6-digit numbers, so it gives us this first part, like 1.02, with move the decimal over 5 spaces. The littler ones, like the 97 and 98,000, 98,000 start here, 1, 2, 3, 4. It only moves over 4 decimal places, so that's why those have a 4. Okay, anyways, our sigma in this problem is 3,200. Our alpha is the same, 0.05. Oh, it said 5%. So just as a reminder, 5% is 0.05. Okay, so now our X bar is given. Oh, we don't have to do this. All of this stuff is given because of the table. There's our Z, there's our P value is 1.2. So let's come back here. Remember, it is a two-tailed test because it's not equal to. And so that means we shade in both the left and the right. It's kind of like a left and right tail test because not equal, we don't know if it's greater than or less than. Okay, so for this, we get a p-value. Oh, let me just go back. My alphas, we already know what these are at. These are at 0.0. And our p-value is greater than alpha. So we should get an image that says do not reject, but let's just look at our picture to make sure. Okay, got it, move on. And so let me zoom in. We can, no matter, let's look at the other side this time because it doesn't matter which side you look at. Our alpha, that's our reject region, the shaded part over here, and our p-value line lands in the middle of this. So this is a do not reject. Our p-value is going to end up being, where did I find some? Somewhere around here. Our p-value is 1.2. So somewhere around here is our p-value. Trying to be fancy and it's just not working out for me today. So our p-value is 0.1259. I'm reading it up here. Up here where it says p-value, but if you can't see that, then just go back and it says the p-value down here, 1.259. Sometimes the question will just say, what is the p-value? So you need to make sure you know how to get the p-value, not just jump straight to the picture, but also look at the picture. Okay, so again, we have concluded that we will not reject. So there, oh, let me just write it on the picture. Since our p-value is here, it is a do not reject situation because our p-value is right in between. There, because it landed in the middle, we are not going to reject. Okay, going back to our conclusion, there is not sufficient evidence to support the claim, and our claim is that the average HR director salary is different than $105,000. Okay, last one. We just have one more to do, but what I want to do is challenge you to do the whole thing. So I'm going to pause it again. You're going to do the one with John as the editor for a local newspaper. So go ahead and work on that problem. And then I'm just going to do it and post the whole answer all at once and just kind of talk through it. But you do it by yourself first, just to make sure that you know how to do it. All right, hopefully you have paused it and got the answer. So let me just show you what I came up with and you can compare. So I have here, I highlighted the claim, I highlighted N. We didn't really need N because the calculator did that for us. Population standard deviation was 9.7 and it is a 10% significance level. And so from our claim, it says less than 30 miles. So mu is equal to, or mu is less than 30 miles for our null and our alternative. Putting all of these values in, including our null and alternative. And whoops, too far back. Okay. Input a data or use a data set. So I used my data set here. I added in the standard deviation of 9.7 and made sure that my alpha was at 0.1 for 10%. When you put 0.10, it doesn't matter. It'll just take off the 0 for you either way. And so it tells me X bar, S, and N. It doesn't ask for that. It's just letting you know. But what we are looking at is either the Z or the P value right here. And here's our P value of 0.0303. So looking at how that affects our picture, I can see that it's less than alpha. I can see that's in the reject region, double checking on the calculator. And here we have alpha. Remember the shaded part, the gray slashes, that's alpha according to this language. And the P value lands us right here. So it is to the left, like I have it listed here, to the left of alpha on this left-tailed test. So we will reject it. It lands in the reject region. In other words, there is sufficient evidence to support the claim because we're rejecting the null, so we're supporting the alternative. There is sufficient evidence to support the claim that the average distance a reader lives is less than 30 miles away. Remember, our claim comes from here, less than 30, or we go back up here. The average distance a reader lives from the newspaper's headquarters is less than 30 miles. Okay, this video was super long because hypothesis testing is super new, but as we go through, just like with confidence intervals, once you learn how to do it, then we just need to learn the different techniques of the different sections. So the next one will have population standard deviation unknown, and then proportion. All right, email me if you have